ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. I am Dr. Shivkumar, Assistant Professor of Physics. So, in this video session, I will be talking about the theory of compound pendulum. It is one of the concepts of the unit rigid body dynamics. So, the important learning objectives are to understand the concept of compound pendulum and its theory. A compound pendulum in general is a rigid mass capable of oscillating about a horizontal axis in a vertical plane. So the point where the axis of rotation intersects the vertical plane of the pendulum passing through the center of gravity is known as the center of suspension. Here O is the point of suspension or center of suspension, and the point G is known as the center of gravity. And let L be the distance between the center of oscillation and the center of gravity. So now at any instant of time in the displaced position, the line OG, that is L, makes an angle theta with the vertical. So now in that position or in the displaced position, so weight of the object mg will be acting in the downward direction. So it can be resolved into two components. One is mg sine theta, which acts as the restoring force or restoring couple, and another component mg cos theta, which will be acting along the line OL. So now, so in the figure, as I mentioned, O is the center of suspension and G is the center of gravity, and OG is equal to L. At any instant, W is equal to mg will be acting in the downward direction. So now in the displaced position, OG makes an angle theta with the vertical. So therefore, the moment of the restoring couple about O is equal to mgl into sine theta. Let I be the moment of inertia of the pendulum about an axis passing through the point O. In that case, the angular acceleration can be written as d square theta divided by dt square. So therefore, the deflecting couple acting on the pendulum at any instant of time is equal to I into d square theta by dt square. So now, so for equilibrium or in equilibrium condition, the deflecting couple must be equal to restoring couple. Here the deflecting couple is I into d square theta by dt square, and restoring couple is minus mgl into sine theta. So where negative sign indicates that the force is directed towards the mean position. Now for small values of theta, sine theta is nearly equal to theta. Therefore, the equation becomes I into d square theta by dt square equal to minus mgl into theta. So taking a term to the left hand side, you will get I into d square theta by dt square plus mgl into theta is equal to 0. If you divide throughout by I, you will get d square theta by dt square plus mgl divided by I into theta equal to 0. So this equation represents simple harmonic motion, and by comparing this equation with the simple harmonic equation, so you will get omega square as mgl divided by I. Therefore, the period of oscillation of the pendulum can be written as t is equal to 2 pi by omega, which is equal to 2 pi into square root of I divided by mgl. Here, the moment of inertia I can be written as Ig plus ml square, where Ig is the moment of inertia about the center of gravity, which can be written as Ig is equal to mk square, where k is the radius of gyration. So therefore, I is equal to mk square plus ml square. So this is written using parallel axis theorem. So now m is common in these two terms. Therefore, m into k square plus l square you will get. Therefore, t can be written as t is equal to 2 pi into square root of m into k square plus l square divided by mgl. This we get by substituting for I in the above equation for period. Therefore, t is equal to 2 pi into square root of k square by l plus l whole divided by g. So therefore, t is equal to 2 pi into square root of L by G, where small l is nothing but k square by capital L plus L. This length is in general known as the length of the equivalent pendulum. So the length of the equivalent pendulum can be defined as, suppose if the period of oscillation of the compound pendulum is same as that of a simple pendulum of length L, then that particular length is known as equivalent length of the compound pendulum. So therefore the period T is equal to 2 pi into square root of L by G, where L is length of the equivalent pendulum. Another important point you need to remember, so that is the point which is at a distance equal to the length of the equivalent pendulum from the center of gravity is called center of oscillation. So here in this particular section we are going to prove the center of suspension and center of oscillation are interchangeable. So when the axis is passing through the center of suspension, L, the length of the equivalent pendulum, is equal to k square by L plus L. Now let us put k square by L as L dash. Then small l is equal to small l plus L dash. So our k square is equal to L into L dash. So when the axis is passing through the center of oscillation, then L becomes k square by L dash plus L dash. Here again k square by L dash is nothing but L. So therefore you will get L as k square by L dash plus L dash. Substituting this in the equation for period, you will get T is equal to 2 pi into square root of k square by L dash plus L dash, or T is equal to 2 pi into square root of L plus L dash divided by G. Here L plus L dash is nothing but the small l length of the equivalent pendulum. So therefore time period T is equal to 2 pi into square root of L by G. So from this it is clear that the time period when the pendulum is suspended about the center of suspension and the time period when the pendulum is suspended about the center of oscillation. So both are same. So this clearly indicates that the center of suspension and center of oscillations are interchangeable. So I hope you have understood the concept of this compound pendulum and then its theory, how that center of oscillation and center of suspension are interchangeable. Thank you.